Welcome to this talk. As you can see in the very first slide, we have a bunch of different images applied with different filters. So the title of the talk is A Lot of Image Filters on Android, and myself Garima Jain, and I am an Android engineer working at a company called Over, which is basically a photo editing app, photo and video. And I'm an Android Google developer expert working out of India. And today we're here to talk about building different image filters on Android. So, who is this talk for? If you have done a little bit image processing on Android, then great. If you have not done any kind of image processing, then that is also fine because this talk doesn't need any prior image processing knowledge. What is this talk going to be about? So, you must have seen these various filter options in these apps. For example, Beauty Plus has all these filter images options, and Google Photos also has its own filter options, and Instagram, of course. So, these options wherein we can choose a different kind of filters and like our input images, the look and feel of these input images changes when we click on different filter. This is image filtering. And you might have also seen some advanced apps, for example Adobe Lightroom, wherein you have the option to do even much more. For example, you can change the hue, saturation, luminance. You can even tweak the curves and all those things to enhance your images. And these are also sort of like a process of filtering your images. So everything like all this, like it is like applying filters to your images to make them look better. So what the talk is going to be about. Firstly, we can look at various approaches in which we can filter images. Then we can go a bit into detail of one of the those approaches, that is using lookup tables. For, of course, because the title itself is like we're going to do image filtering using lookup tables. So then we're going to look into detail about applying these LUT image filters. We are going to look at a method, Renderscript, which is a framework which is uh, available in Android. We're going to briefly visit various challenges that we faced while implementing image filters. We are going to briefly visit the OpenGL implementation, and we're going to do all that, and we're going to try to make it fun, and let's see how we do. So, without further ado, let's go into the very first topic of this presentation, that is different approaches to image filters. So there are different approaches that we can take when applying image filters, like when implementing this, or like if thinking from a product point of view also, like should we go with preset, should we go with LUT. So let's look at like these options first. So presets. So we just saw that like certain apps provide us with a bunch of these different tweaks that we can do, which are pretty complex, and we can do a lot of things. For example, in this particular app, so these kind of all these kind of uh, all these kind of features, they're actually map to this kind of a JSON structure, because like what we are ultimately doing is we are tweaking all these little values, and these little values are then stored somewhere like in the form of filters. Like a filter is nothing but a combination of all these presets. So this kind of image filter storing technique is called using presets. So that is great. Like if we use presets for our image filter application, then we can provide the user with like all these values, and we can keep on adding these values, and like user can do a bunch of things, like user can tweak curves, like there is like no limitation to what a user can do, and it can get really complex. So presets are good. We can achieve great results with presets. There are lots of customizable options. But from product point of view, when we were implementing it, we started thinking like, do we even need it? Actually, we needed something to ship faster. We are a content creation tool, and our product requirement at that point was like, we need the user to be able to create certain graphic, something, and user needs to get that done quickly. And our target audience is n- at the moment is not like those people are actually who actually need all those advanced options. And adding new types of presets, like for example, we have a bunch of options, and if you want to add another option, it is a bit tough, especially in a cross-platform company. Like we were a cross-platform company, so if we wanted to add another preset, Android needs to know how to interpret that preset. At the same time, iOS also needs to implement the same thing, and also web needs to implement the same thing. All the platforms need to know this new kind of preset. Whereas this is not the case with LUTs. LUTs are like just one algorithm which each platform can implement. Uh, and we need to perfect just one algorithm instead of perfecting all these algorithms for different presets. So, what are LUTs? Like I keep talking about them. LUTs are basically lookup tables. For example, like let's take presets out of our mind. From a fresh start, we have an input image and we have a lookup table. Like this is how a lookup table looks like. It has a bunch of color values. So basically, given a pixel value in our input image, it will map to a certain color in this lookup table. And instead of taking this input pixel, we take this mapped pixel value and we create the output image. So we do the same thing for each pixel in this image, and that is how input image gets mapped to a filtered output image. Like each color maps to a different color. So LUTs basically replace runtime communication with simpler array indexing operations. Like if we if we represent a particular LUT in form of arrays, then it becomes a simple array indexing operation. Like we just need to look up a color. On the other hand, if we talk about presets, presets are basically at runtime we need to render a particular algorithm, and that so this like LUTs become a bit faster because like we're just doing array indexing in this case. So we have different kinds of LUT tables. We have 1D, we have 3 cross 1D, 3D. We need 3D, but like let's still mention different kind of lookup tables. So this is a very basic like 1D lookup table, which is a 1D array, and we have index on left, and the color that it maps to is this. This is a very limited option because if we can map only four uh, we can map to only four colors. So let's take three arrays instead, three 1D arrays, which is three 1D lookup tables, each for one channel. This is red, green, and blue. And even then, it is going to be pretty limited. In the image processing world, what we actually need is a 3D lookup table, like something like this cube. We will have on the 0, 0 axis, we will have all the color values starting from here, and this cube is going to be filled with color values. And in this case, like this cube is like 4 cube, and this is an example. So this is how it's going to be. So given values ranging from 0 to 3, we can map all the different values over here, and this is how the 4 cube identity lookup table would look like. Because given an input pixel 000, we are going to map to black, and given an output pixel 3 input pixel 333, we are going to map to white. So this is like just like an identity matrix. An identity LUT is like, given an input image, it should give an output pretty much closer to the input image. Like, when I say pretty much closer is like, we'll understand that later, but like the input image and the output image looks pretty much similar. So that is an identity LUT. So in image processing world, 4 cross 4 is probably not good enough, as you might have already guessed. Practically, in for practical purposes, we use 64 cube LUT images. 64 cube LUT images can map these many different colors. So this is an example of an identity 64 cube image, which is 512 cross 512 in dimensions. So we have these 64 squares and all these things. So how this LUT fits in our designer's pipeline? So designers are going to create filters using these LUTs, and what they're going to do is they're going to start with this identity LUT image, which maps each input image just the way it is into an output image. What they're going to do is, given an LUT image, they're going to apply various effects to it. Then, after applying an effect, they're going to export and create all these different LUTs, and then we can take those LUTs, and instead of applying all these presets and calculating the output values, we can just look up the output values for new filters. And this is how we can create a bunch of new filters using like however more LUT filters that we want. And using LUTs, designers can also easily create new filters. And if the designers want to use a new kind of a preset on their end, they will want to try out a new tool, they can easily do that. Because we do not care about presets, we do not care about existing algorithms. All we care about is just one algorithm, that is these lookup table algorithm. So now let us look at this algorithm itself. So with LUTs, like, we need to make this algorithm perfect, and this needs to be uh, a perfect algorithm, because this is the only algorithm which needs to be implemented across platforms. So when we started implementing these filters, the first thing that I looked at was like, oh, maybe there is a library out there which does this for us, and I came across this easy LUT library, and I was really happy. And my dreams got shattered when I got to know that this easy LUT library internally actually uses getPixel and setPixel Java API, which is not so fast because it runs on the CPU. So getPixel would iterate over all the pixels of an image, and you can imagine they're like, if we're living in 2020 and how many pixels are now in our images. So yeah, basically like iterating them on CPU is probably not a good idea. So if you want to know more about various image processing techniques, and if you do not want to make the same mistake that I did, you should probably watch these talks beforehand, which I didn't do. And there's another talk from my colleague Rebecca. And basically the gist of these talks, let me try to give it to you. So we have different image processing techniques. In Java, getPixel setPixel is probably not the right thing to do. We have something else called Renderscript, which, instead of working on CPU, it can work in parallel using, and it can utilize our GPU if available. And then we have OpenGL, which is even faster than Renderscript. So basically, this is the gist of it if you're interested. And if you're interested in more details, please check out those talks. So at that time, we were already using Renderscript. So we went ahead with the Renderscript solution because migrating to OpenGL is a task in itself. And I was definitely not the right person to do this. So we firstly started with the render script, but like most of the concepts with the render script also map to OpenGL. So if you are interested straight away in implementing an OpenGL, then the coming up concepts will also help you out because like they're pretty much the same. So render script, so they're basically different kind of approaches with which I found. Firstly, like there's a built-in class called script intrinsic 3D LUT, or I could create a custom script. But like when we have something out of the box, why not use it? So I went ahead and looked at like the script intrinsic 3D LUT. So this is the definition that I got out of developer Android. So script intrinsic 3D LUT. It is intrinsic for converting RGB to RGBA by using a 3D lookup table. Looks like exactly what we need. The incoming RGB values are used as normalized XYZ coordinates into a 3D allocation. Great. The 8 nearest values are sampled and linearly interpolated. Looks even better. The result is then placed in the output. Awesome. Looks like exactly what we need. So then I started looking at the API. So with the render script, we allocate memory, and like uh, this is what an allocation is. So basically, in order to set LUT to our script, I need to call this function, and I need to provide an allocation of our lookup table. So how do I create this allocation now? When I started looking, I found these like various different APIs, and I have this image, like how do I, which function do I use? And the documentation, I'm sorry to say, but like isn't that much clear. So I started looking around and I couldn't find it. But then like this helpful person has this easy RS implementation, which basically pointed out at the right function that I need to do. I probably still do not know how this function is different from the others, but like this is the right one. If you want to check out yourself how to do this, you can check out this easy RS implementation. Then this is how we can use the script intrinsic and render script. We create this intrinsic, we set the allocation that we just created, and then we just basically run this script for each, and we provided the output allocation, and we are good. Like we just implemented LUT image filters and we are so happy. So, working in a cross-platform team, one of my colleagues, they suggested that let's pass like these results through various a bunch of tests. The first one was transparent test, that is given an a transparent input image. These are a set defined of results, and I should also probably be getting the same results because like I've implemented it. And it turned out my transparent test failed. And as it turns out, script intrinsic 3D LUT doesn't support alpha values that great. And if like that's the case, should they not put this in the documentation itself? Turns out they did in a hidden way. So intrinsic for converting RGB to RGB alpha. There is no alpha component in the input, or maybe like we can still process alpha values. I'm still not sure. Like if you find out a way to process alpha values, so for just for my for the sake of my sanity, please let me know. But I had to throw away that solution and I instead uh, move to come to this one because I couldn't find a way at that time. So custom script should be pretty straightforward. What we actually need to do is, and it should also be tweakable, so that should be good. So with custom script, we need to take each pixel value and we need to find that corresponding value in the LUT image and use that value instead. So let us draw out a diagram of our custom script and where it fits in our pipeline. We have a given input image, we have a given LUT. For all pixels in input image, what we'll do is we'll take the value RGB, you'll find the corresponding pixel in this LUT image. We will save all the updated pixels in the output bitmap, and we will do basically the same thing for all input pixels, and that is how we will get the output bitmap. So we need to do this. So rest of the steps are pretty straightforward if we're working with the Renderscript. This is the only place where custom script fits in. So we need to write a script for this in Renderscript. So looking up a pixel in LUT. So this is how our LUT looks like. So if I tell you I need to find where value 127 comma 127 comma 127 is stored, it's not so straightforward uh, to find and to know like how to look up a pixel value in this, and that is probably the most challenging thing. That was the most challenging thing for me, and I couldn't find any documentation out there to do this mapping. And even if I could find it, it was a bit hidden and it was not explained very well, and this is probably why I'm doing this talk, so that I can share this particular information with everyone. So if you look closely, this is how LUTs look like. So the red channel within each box increases from left to right. Green channel within each box increases from 0 to 1 in from top to bottom. And this blue channel increases from this leftmost box to this bottommost box. Great. So this is basically the lookup algorithm. Like we get the blue value of a particular input pixel, and that gives us the box. And once we find the box, then x and y within that particular box is our green and red values. So let us take an example. We have an input pixel 127, 127, 127. Since we have a 64 LUT and our input pixel and pixel values are in the range of 0 to 255, so each four values will just map to one value in the 64 LUT. So we divide by our input values by 4, so we get this. So blue should give me the 31st square, and within that 31st square I need to look at the green and red values. So this x and y should give me the exact output value that I need to use. So in pictorial form, blue should give me the 31st square, and within the square the R and G values should give me the correct output value that I need to choose. So that is great. But what computer understands is, or my Android API is like how to read a value from this. I need to transform this algorithm, this pictorial thing that we saw, in terms of x and y values. And as it turns out, and if you look closely, this maps to this particular algorithm. That is, x is given by this and y is given by this. So let's once we have calculated x and y, we can plug it into the render script. This function particularly does all the GPU magic for us. Alpha remains the same for output image, and RGB is given by running all the lookups in parallel using GPU. And our custom script works. We are so happy. What we have just implemented is we looked up all the RGB values, we found those values in corresponding LUT image, we saved the output bitmap, and that is how we got our output values. So the dreaded transparent trace, let's put our results through this. So as it turns out, we failed again, even though we did set the alpha. But why now? It was a bit frustrating, but uh, we learned that there's something called pre-multiplied alpha, So, what is pre-multiplied alpha? So, whenever we are dealing with alpha images in Android, so Android, you can like learn more about it in this blog, The Curious Case of Android Pre-Multiplied Alpha. That is how I learned it, and also from the help of my colleagues. So, when Android is saving an image which has alpha in it, what it does is, like for example, if we want to like blend these two images, like what Android would do is like with these calculations, like we have like these constant values, like the source is getting multiplied by alpha, and Android figures out that this value is pretty much a constant. So what it does is, instead of saving our input image with alpha value, with exactly. What Android does is it pre-multiplies value. When an image has an alpha value in Android, instead of saving the RGB values as it multiplies the alpha with it to simplify, to optimize like a bit of calculations for performance issue purposes. So the issue is, when we are looking an input pixel, we're looking up the wrong value lookup, because like our input images are already multiplied by alpha. So the solution over here is like, one thing I could find is like, while loading up a bitmap, I could set pre-multiplied to false, but then I thought like it would turn off the optimizations. That probably what we don't want to do. So instead, what we can do is, we already have a custom script. It is pretty much tweakable. So why not tweak it ourselves? So we would fit another step in our pipeline, that is like, after looking up a pixel value, we would firstly unpre-multiply, because it is already multiplied by alpha. So we will take out that value. How we can do that is pretty much straightforward calculations. We can get modified R by taking out the alpha. So once we have modify R, we instead of using exact RGB values to get X and Y, we get use modified RGB values, and we use this X and Y again. And after plugging that into our script, we now pass a transparent image through our script, and finally it passed the transparent test, and we are so happy, but not so fast. So even though like everything is working, but like there were a few more hurdles that we had to face. For example, banding and interpolation. So this is how in some cases our output images look like. So like there is a bit of banding. Let me zoom in a little bit for you. So these kind of artifacts we could see in our filtered images. So what happened was, I probably hinted a little bit on it. Like our input images, they have RGB channels ranging from 0 to 255, whereas our LUT bitmap, LUT images, they can map only 64 cube colors. Like every four color map to a single color in LUT images. So so if you remember, when we looked up a pixel, we had to divide by 4. So this is what is causing all these banding issues. 64 LUT images can only map uh, these many colors, whereas input PNGs have a lot more colors. So clearly, 64 LUT is a lossy technique. So the solution to fix this problem is, when a color value is when we are looking up a color value, and instead of dividing it by 4, and then we either need to take the seal value or a floor value, what we can do is we can take 2 points and we can interpolate between those two. So interpolation is just that. Given, like for example, in linear interpolation, if we had 2 points, we can interpolate between the two. But we are dealing with images here, so we are not dealing in terms of like just 2 points. In 2D world, we are dealing with points in 3D world, so we probably need trilinear interpolation. So if you want to look at the implementation, you can read this good book by Henry Kang. That's what we did. And then we implemented this linear interpolation into our custom script. And uh, you can look at like a bit more about this. And this was the output without interpolation with some banding, and with interpolation you can see like we have reduced this issue uh, to some extent, and if we want to improve this further we can use a better interpolation technique or so, and so on. So yeah, it works. So what we just did, we added another step, like after finding a corresponding pixel in LUT image, or like many more pixel, many more pixels if you go into the details of trilinear interpolations, we interpolate between those values and take that value instead. So there were this was fixed, but like there were other tiny teeny issues. For example, like the stack trace with the Renderscript is just too good. So this was one error that I was getting, like some faulty address kind of a thing, and like I had to look at some hex code. Just kidding. Of course, I didn't do that. But like 2 more days later, it turned out like it was just an array index out of bounds. So I mean, the point is like the errors can like trouble us a little bit. So that was a bit challenging. Then the next challenge was like, until now in this talk we have been expecting and talking about square LUT images, and so that is what we expected to get like from our designers. But in reality, the world is not that, I mean, straightforward. So this is what we got instead in reality. And so there is no need to panic. I mean, this is nothing too different that we just talked about. Like everything that you just learned till now still works. There is a just a teeny tiny difference. That is like hand LUT is just a different kind of a format instead of square LUT, and a different kind of way of looking at like these distributions, and a different algorithmic formula instead of that one. So I think I had to break my brain to get this formula because I couldn't find it anywhere. So again, the reason of me doing this talk, you can use this formula and thank me at some point of time. I hope, I wish somebody benefits out of some, gets something out of it. But anyway, like we can plug this formula in our previous step and we are good. I promise there's nothing else to do. And we plug that in and we are so happy. So finally, we were able to build this kind of UI, like these kind of many filters that can be applied to our input images. And this was the very first version. Now we have evolved to a different version and the UI is different. And we were also able to apply this to another feature. Spoiler alert, we'll come to it. So we just implemented image filters using Renderscript, and then like sometime back we evolved from Renderscript to OpenGL because like of various reasons. So we can do the same thing using shaders. OpenGL is not too much different. All the like things that we learned, like unpre-multiplying, looking up, still apply. We just get a bunch of goodies with OpenGL. Interpolation support, that is out of the box. Yeah, we don't have to look at those cubes and read that book. And it also runs on GPU and it is even faster than Renderscript. If you want to know why, you should probably ping my colleague. Please don't ask me, I don't know why. So brings us to the end of this talk. I'll point out a few references, which if you're interested, you can look at all this. This helped me. And if you want to explore further, there is another talk which my colleague did, Wayne, and he built the same, like the like all those tests, like that we did transparent test. So he built that using Go. So we had a reference implementation to look at. And there is another file format which we could support, that is cube format. and we could use a better interpolation technique to get even better results. So, to conclude, if we have an input image with LUTs, we can create so many LUTs. Like the designers get the power of creating so many, creating and shipping a lot more features, like a lot more filters, very easily once we have implemented the solution, and this fit right in the product vision at that point. And also, like we can ship like things faster, like we were able to ship filters faster using lookup tables. So given input image and a lot of image filters, we can create a lot of image filtered output images on Android. And this brings me to the end of this talk. Thank you, and if you have any questions, please uh, let me know.